Good morning, students. How are you this morning? Welcome to the continuation of the lecture on acid and bases. Let me quickly do a recap of what we have done so far, very briefly, before we continue with the lecture today. We started with the three definitions of acid and bases under the Arrhenius concept, the Brusselot concept, and the Lewis concept. And I remember that I told you that an acid, according to Arrhenius, is defined as a substance when dissolved in water, increases the concentration of hydrozonium ion or hydrogen ion, okay? Or we can equally define Arrhenius' definition of an acid as any substance that produces hydrozonium ion or hydrogen ion when it comes in contact with water. Arrhenius base can also be defined as any substance when dissolved in water increases the concentration of hydroxy ion. Or we simply say that when a base is dissolved in water, it produces hydroxy ion. So that is the definition of acid and base under the Arrhenius concept. For Brusselot, we define an acid as any species that donates proton, okay, that donate proton in water in a proton transfer reaction, while a base is any species that accepts proton. That is the definition of Brusselot of acid and base. And the same concept, Brusselot talks about an acid when it donates a proton, produces a conjugate base, while a base, when it accepts a proton, produces a conjugate acid. So for acid and base that differ in the presence or absence of a proton, it is called a conjugate acid-base pair. So what gave birth to a conjugate acid is a base that has accepted proton. And also what gave birth to a conjugate base is an acid that has loses a proton. So that is the recap of Brusselot. Now for Lewis' definition, Lewis defined an acid as an electron pair acceptor and a base as an electron pair donor. And in the transfer of electron pairs from a base to an acid, a covalent bond is always formed. We discussed all that. Then we also talk about aphoteric substances. We said any substance that is capable of acting either as an acid or a base are said to be aphoteric. And a typical example of this is the water. Water has the ability to produce hydroxy ion in water or produces hydrozonium ion in water. So it's fall under the theory concept of acid-base definition. In other words, according to Arrhenius, water increases hydroxy ion or hydrogen ions when it's self-ionized, when it undergoes auto-ionization. And it also has the ability to donate and accept a proton, according to Brusselot. It also has the ability to donate and accept electron pair, according to Lewis acid. So we also talked about the strength of acid and bases, and we said that the strength of an acid is majorly determined by the level of dissociation, the ability of the acid to dissociate completely or partially in water. And so we say that the strength of an acid refers to the ability or the tendency to lose a proton when it comes in contact with water, while the strength of a base refers to the ability to accept proton. So a strong acid is one that completely dissociates when it comes in contact with water, while a weak acid partially dissociates when it comes in contact with water. And we also said that there are certain factors that affect the strength of an acid. We measure the polarity of the bond, we talked about the strength of the bond, and we talked about the stability of the conjugate base. Then from there, we talk about oxy acid, that there are acids can be classified in terms of those that does not have oxygen and those that have oxygen in their compound structure. And that we said that an acid that have oxygen in their compound structure, like nitric acid or phosphoric acid, they are known as oxy acids. Okay, then from there we talk about polyprotic acids or basicity of an acid. And we mentioned that an acid, when it donates a proton, when it gives a proton or donates a proton in water, it is monoprotic. We call it monoprotic or monobasic. And when it gives out 2 protons in water, we say it is dibasic or diprotic. When it gives out 3 protons in water, we say it is tribasic or triprotic. So, however, when an acid gives out protons 2 or more, we say it is polyprotic. So we need to take note of that. So that is all about the polyprotic of an acid. Then we equally went further to talk about the octoionization of water, that water has the ability to undergo self-ionization. And so we said that water can function as an acid and can function as a base. And there is a concept, a very important concept, which is called the ionic product of water, or we call it the dissociation constant of water, which is K subscript W. K subscript W is equal to the concentration of hydrogen ions multiplied by the concentration of hydrogen ion. That equation is very, very important for calculation. And we said it is temperature dependent. So temperature affects the value of Kw. So whenever Kw is being measured, the temperature of the room determines the value that you get. So we did a lot of calculations using the K subscript W. And we said that an acid could be neutral, an acid could be, we said that there are 3 situations where water could be neutral, water could be acidic, and water could be basic, depending on the concentration of the hydrozonium ion and the hydroxy ion. So we did a lot of calculations on that. And then we talk about the pH, and we said the pH is the negative logarithm of hydrogen ion concentration. And we did some little examples on how to calculate the pH, and we can also calculate the pOH also by saying that the pOH is equal to the negative logarithm of hydroxy ion concentration, and also pK is equal to the negative logarithm of K, which is the equilibrium constant. And so we use those 3 formula, the KW formula, the pH formula, the pOH formula, to work a lot of examples during our previous lecture. Okay, so we also talked about how to measure the pH, and we said that there are 3 ways by which the pH of a solution can be measured. Number 1, we use the pH meter. Number 2, we use the acid-base indicators. And number 3, we have the paper stripes. Then we also talked about how to calculate the pH of a strong acid. We did all that. Then after that, we talked about the ionization percentage, the percentage ionization. That's we talked about the pH ion. We said the percent ionization is the concentration ionizable over the concentration, the original concentration. Okay, the concentration that is ionizable and the original concentration multiplied by 100% over 1. That is the percent ionization. That is how to calculate the percent ionization. So we gave 1 or 2 examples on how to calculate all that. So that is all we've done so far. And in our continuation of the class this morning, we are talking about polyprotic acid and acid salts. Polyprotic acid and acid salt. And remember, I told you that polyprotic acid are acids that have the ability to undergo ionization more than once, maybe twice or 3 times or more. Okay, and if they are doing that, they do it step by step. A polyprotic acid that gives out 2 or 3 protons, when it comes in contact with water, undergoes ionization step by steps. It loses the first proton, it loses the second proton, and the third proton, and so on and so forth. And as it's donating this proton successively, it will give rise to the K value. It will give rise to the dissociation constant value. And so for the first proton that is donated, there is a K value for it. For the second proton that is donated, there is K value for it. So the first one is donated as Ka1, the second one Ka2, and every successive one will be designated with the figure Ka2, Ka3, Ka4, just like that. But it's important for you to know that the K value of the first proton that is given will usually have the highest number because it is easy to undergo dissociation. The level of dissociation or the ability of dissociation of the first proton is always very high. And that is why the K value is always very high compared to every other successive value, okay, of the K. So now you may be having problems or questions where you are asked to calculate the pH of a polyprotic acid, and they will give you the K1 value, give you the K2 value, give you the K3 value, and so on. In such a situation, let me show you how you do that. Now, there's a question before us here that says, calculate the pH of 0.037 molar carbonic acid, H2CO3. You are provided with the K value dissociation constant. So you have the first dissociation constant, Ka1, which is 4.3 times 10 raised to power minus 7. You have the second dissociation constant, Ka2, which is given as 5.6 times 10 raised to power minus 11. Okay, so you have Ka1, you have Ka2 that is provided in that question. And one thing that you must know when you are asked to calculate the pH of an acid, for example, the one we have before us, that has the ability to donate 2 protons in water, like I said, it donates the proton one after the other. And so we can decide to calculate the pH of the acid considering the first dissociation constant or using the first dissociation constant, K1. So we may not need to use K2, we'll just use the first dissociation constant, K1. And you know the formula of dissociation constant. Dissociation constant is the product of the concentration of, concentrations of the ions in water when the acid undergoes ionization over the concentration of the acid itself. If you look at the formula before us, Ka1 is equal to the concentration of the hydrogen ion and the carbonic ion. If you look at that equation, the carbonic acid, when it undergoes ionization, it produces hydrogen ion and the carbonic anion. And so the K value now will now be the concentration of the ions, the products, over the concentration of the reactants. And we said that K1 value is equal to 4.3 times 10 raised to power minus 7. Okay, so now, and that is equal to, remember we said that the concentration of the ions are equal to each other. That is, the hydrogen ion is equal to the concentration of the anion, the carbonic anion. And so that's why we say S multiplied by S in the numerator, if you look at it carefully, over the concentration of the acid. And because our Ka1 value is small, we can assume that 0.0037 minus X is equal to 0.0037. Okay? If that assumption is okay, then we make S squared the subject of the formula. And that will become 0.0037 multiplied by 4.3 times 10 raised to power minus 7. Hello, sir. Hello? times 10 raised to power minus 7. And so if we do the evaluation, S becomes the square root of that 0.0037 multiplied by 4.3 times 10 raised to power minus 7. If you look for the square root, it will now be 4.0 times 10 raised to power minus 5. So the pH that you will not substitute the value into the negative log of hydrogen ion concentration. Remember, we said the hydrogen ion concentration is equal to the carbonic anion concentration. And so we substitute the value into the pH formula, pH, which is the negative logarithm of hydrogen ion concentration. So if you substitute that value, it becomes pH is equal to negative log of 4.0 times 10 raised to power minus 5. And if you do that and you work out that evaluation, you will now get your answer of the pH. You will now get the answer of the pH value. Okay. So there is another calculation here. It's just the same step. Here you are told to calculate the pH of 0.037 of the same carbonic acid. You are provided with K1 and Ka2, so you can follow the same procedure. What we did in the first calculation is to use the first dissociation constant value to evaluate. Okay, here we are showing you an example where we can use the second dissociation constant value for calculation. Remember, in using either first or second dissociation constant, you must also use the right equation along. If you are using the first dissociation constant, you use the first equation, okay, when carbonic acid undergo ionization to give out the first proton. But when you want to use the second dissociation constant, what you do is to use the second ionization equation, where the carbonic anion will further undergo ionization to give out the hydrogen that is left in the compound. And that is what you are seeing before us, the equation, the carbonic anion HC3, HCO3 minus, okay, we give you hydrogen plus CO3 2 minus. Okay, so we can now determine the concentration of CO3 2 minus. But remember, we always say that the concentration of the two products, the ions that are in solution, the hydrogen ion and the carbonic ion, they are always equal to each other. And we've done this calculation, okay, of the concentration in our previous, the last question that we solved. Okay, so if we know the value already, it's just to substitute them into the equation, then you get your concentration for the carbonic acid. So now let's consider weak bases. Let's consider weak bases. We've considered how to calculate the pH of strong bases, okay, polyprotic acids, how to calculate the pH of polyprotic acid, acids that donate 2 or more hydrogen ions when they come in contact with water. And now we want to look at how to deal with the one for weak bases, And we have said that weak bases dissociate partially in water. The reason why they are weak is because that dissociation is partial. So the general reaction of acid-base water is what we are seeing there, and the hydrogen ion will be given. So when a base reacts with water, it gives out hydrogen ion. The concentration of the hydrogen ion increases. And so if we want to develop an equilibrium constant, a dissociation constant, the equation will be that of the anion, that of the ions in solution over that of the base, as you can see in the formula before you. So that Kb is called the base dissociation constant. The base dissociation constant, and is equal to the concentration of the ions in solution, positive and negative, over the concentration of the base. The pH is determined from the concentration of the hydrogen ion. So how do we do that now? So there's an example here to explain how to go about that. Now, you have a question before you. The question says, calculate the pH of a 0.15 molar solution of ammonia. and you are provided with the Kb to be 1.8 times 10 raised to the power minus 5. So when ammonia, which is a base, comes in contact with water, the equation is there, it will give you the ammonium ion and the hydroxy ion. Okay, the Kb will be the multiplication of the concentration of the ions in solution over the concentration of the ammonia. Okay, like I've mentioned before, the concentration of the ions in solution are equal to each other. The positively charged and the negatively charged, the concentration of the cations and the anions are equal to each other. And we say if the concentration is X, then we can now say S multiplied by S because they are equal to each other over the concentration of the base. The concentration of the base, which is the ammonia that is provided for us in the question, is 0.15. So it will become S multiplied by S over 0.15 is equal to Kb. And remember, Kb has been given to us in the question. Kb is 1.8 times 10 raised to the power minus 5. And so if we do that, it becomes Kb 1.8 times 10 raised to the power minus 5 is equal to S squared over 0.15. And if that is done, we make S squared the subject of the formula, and we can now evaluate for S. So S becomes the square root of 0.15 multiplied by 1.5 times 10 raised to the power minus 5. And if that is done, you have the answer to be 1.6 times 10 raised to the power minus 3. That is the concentration of the hydroxy ion. And so if we know the concentration of the hydroxy ion from our evaluation, we can now use the formula for pOH to evaluate the pOH of the hydroxy ion concentration. Remember, we said that pOH is the negative log of the hydroxy ion concentration. And if that is done, it becomes minus log of 1.6 times 10 raised to the power minus 3. Remember, the 1.6 times 10 raised to the power minus 3 is the concentration of the hydroxy ion. And so if we evaluate minus log of 1.6 times 10 raised to the power minus 3, it will give us 2.8. That means that the pOH is 2.8. But what we are asked to evaluate is the pH, not the pOH. So we are not stopping at pOH. But remember, there's a basic formula that is very, very important for you to know. And that formula says that pH plus pOH is equal to 14. We've explained how how we arrive at that in our previous lecture. And so if we know the value pH, if you know the value pOH, we can now, from that formula, look for pOH. So we say pH will now be 14 minus pOH. If we do that, it becomes pH is equal to 14 minus 2.8. And that's why we give us the pH of the ammonia solution to be 11.2. So that is how to calculate the pH of a weak base. The pH of a weak base, where the Kb is given and the concentration of the solution is given. Now, another very important equation that you need to know is the relationship between Ka and Kb, that is the acid dissociation constant and the base dissociation constant. How did we arrive at this? Okay, now consider a base. A base, for example, a weak base, for example, ammonia, when it dissolves in water, it will give you ammonium ion and hydroxy ion. So if you write the equation for the Kb, that will be the concentration of the cations and the anions in solution. Okay, you multiply them over that of the concentration of the base. The formula is there before you. Okay, so the conjugate acid of the ammonia solution can undergo further reaction with water to give you the ammonia and hydrogen ion. And so if you now write the acid base, the acid dissociation constant, it will give you the ammonia, that is the product, the concentration of the ammonia and the hydrogen ion over that of the ammonium ion. Okay, so if you add these equations together, then it becomes the equilibrium constant. If you add the two equations together, it becomes Ka multiplied by Kb to give you the two equations, the multiplication of the two equations. Okay, so if you cancel out Ammonium will cancel out with the ammonia will cancel out with the ammonia. So what is remaining from those equations will now be the concentration of the hydrozonium ion multiplied by the concentration of the hydroxy ion. Remember, we said the multiplication of the hydrozonium and the hydroxy ion will give you Kw, a very important formula in this study. Okay, if that is the case, what it means is that your Ka multiplied by your Kb will equally give you Kw. So this is another formula that we've developed now, and this formula is very, very important. What is the formula? That Kw is equal to Ka multiplied by Kb. So you might have a question where Kw is provided and Ka is provided, and you are asked to calculate Kb. May I recap for a while and give you some of the basic formulas that we've discussed in this study that is very, very important. The formulas or the equations that are very important for you to remember. Number one, we said that Kw is equal to the multiplication of the concentrations of the hydrozonium ion and the hydroxy ion. That is the first one. And number two, we say the pH is equal to the negative log of hydrogen ions. That is number two. Number three, we say that the pOH is equal to the negative log of the hydrogen ion concentration. Number four, we talked about now the Ka multiplied by Kb is equal to Kw. Very, very important. You must remember these formulas for calculation, for the purpose of calculations. So the product of the acid dissociation constant for an acid and the base dissociation constant for the conjugate base is equal to the ionic product of water, or the dissociation constant of water. So if one is known, maybe the Ka is known, okay, you can calculate for Kb. Or if Kb is known, you can calculate for Ka. But one thing that is important here that you must also know is that as the strength of an acid increases, the Ka value, that is the acid dissociation constant, will equally increase. Okay, so the strength of its conjugate base must decrease. In other words, as Ka is increasing, the Kb must decrease. So we have a question before us just to further explain that concept of Kw is equal to Ka multiplied by Kb. There's a question here. Given Ka is equal to 6.8 times 10 raised to the power minus 4 for hydrogen fluoride at 25 degrees C, calculate Kb for the fluoride anion. Remember the formula Ka multiplied by Kb is equal to Kw. We have been provided with Ka, so we know the value of Kw is a constant 1.0 times 10 raised to the power minus 14. So we make Kb the subject of the formula. It becomes Kw over Ka. And so if we evaluate that, we substitute Kw 1.0 times 10 raised to the power minus 14 divided by Ka that has been provided for us in the question 6.8 times 10 raised to the power minus 4. We arrive at 1.5 times 10 raised to the power minus 11 as the value for the Kb. And so you have other examples like that you can easily solve. If we know Kb, we can evaluate Ka. If we know Ka, we can evaluate Kb. Kw is a constant value, 1.0 times 10 raised to the power minus 14. Okay, we are moving on. Let's quickly look at acid-base properties of salt solutions. The acid-base properties of salt solutions. Remember that a salt can be regarded as an ionic compound obtained by the neutralization reaction in aqueous solution. Okay, a salt is obtained from neutralization reaction when an acid comes in contact with a base. So the resulting salt solution may be neutral, may be acidic, or basic. When a salt dissociates in water, okay, it gives you cations and anions. In other words, it will dissociate to give you the positively charged and the negatively charged. For example, you have sodium chloride, your common table salt at home. When it undergoes dissociation, it will give you the sodium plus and the chlorine minus. So you have positively charged and negatively charged ions in solution. So these cations and anions, they further react with water to generate the hydroxy ion or the hydrozonium ions. So you have the H3O plus, which is the hydrozonium ion, or the OH minus, which is the hydroxy ion. This kind of reaction, where the ions of the salt in solution undergo further reaction with water to give you hydrozonium ions and the hydroxy ion in solution, we call this hydrolysis. This kind of reaction is called hydrolysis. When a salt in water, the ions and the cations, the anions and the cations undergoes further reaction with water to give you the hydrozonium ions or the hydrogen ions. Such a reaction, we refer to it as hydrolysis. So the reaction of an anion with water, like we've been explaining, we produce a conjugate acid and hydroxy ion, or the conjugate base and the hydrozonium ion. Okay, so now the pH of the salts depends on the nature of the cations and the anions that are in solution. So let's look at a situation where the anion from the salt reacts with water. The anion from the salt reacts with water. Let's look at the situation. Now, what happens here is that you now have a conjugate base of the acid. You know, an anion carries a negative charge. When a salt dissociates with water, like I said, it gives you negative ions, it gives you positive ions. So the negative ion carries negative charge. And we regard to that as the conjugate base of the acid. Okay, conjugate base of the acid. So there are two situations here, two possibilities. Yeah, the acid may be strong or the acid may be weak. So if the acid is one of the acids that we have listed and it's not easily hydrolyzable because it's very strong, the bonding is strong, okay, it will not affect the pH of the solution. It won't affect the pH of the solution. But if the acid is not one of the strong acids that we've listed here, then that means that the acid is a weak one. It's a weak one. And in this case, the conjugate base will also be a weak base. The conjugate base will be a weak base. And the fact that it's weak, the extent of reaction with water will be small, and it will produce a weak acid and an hydroxy ions. Okay, so such ions generate the hydroxy ions in solution and increases the pH of the solution, making it basic. Okay, so when an anion reacts with water, it increases the pH of that solution, particularly when it is weak, and it will make it to be basic. Okay, it makes it to be basic. So when a chloride ion reacts with water, a chloride ion reacts with water, there will be no reaction. Okay, but when acetic acid, an acetic acid anion reacts with water, it will produce the acid and hydroxy ion in solution. So let's look at a situation where we have reactions of cations with water. Reactions of cation with water. We've talked about the reaction of the anions with water, and we say it makes the solution to be basic and it increases the pH of the solution. Now, in this case, it is important for you to know that cations reduce the pH of water. Cations reduce the pH of water. So polyatomic cations, that have 2 to 3 charges, okay, containing 1 or more protons, can be considered to be the conjugate acid of the weak bases, the conjugate acids of the weak bases. Okay, so for example, now let's have an ammonium ion okay, reacting with water. So in this case, it will produce the ammonia and the hydrozonium ions. So the cations of strong acids do not hydrolyze in water, particularly for the group 1 and for the group 2 metals, they do not hydrolyze in water. And that is why if you look at the slide before you, you will notice that sodium ions in water will produce nothing. There will be no reaction because the cations of strong bases, okay, do not hydrolyze in water, particularly for metals of the group 1 and the group 2. Most metal cations that are hydrated in solution also lower pH. Okay, metal cations that are hydrated, okay, lowers the pH of the solution. So they act by associating with water to release hydrozonium ions. Okay, so you can see a metal that is hydrated. Okay, here aluminium that is hydrated with water, aluminium hexahydrate 3+, okay, reacting with water to give you the base and hydrozonium ion. It produces the base and the hydrozonium ions. So let's quickly look at how to predict the pH of a salt. How do we predict the pH of a salt? A salt of a strong base and the salt of a strong acid has no hydrolyzable ions. Okay? Has no hydrolyzable ions. And what that means, it gives rise to a neutral aqueous solution. What we are saying is that when you have the ions in solution of a strong, the salt of a strong base, or the salt of a strong acid, any salt that is coming from a strong acid or from a strong base, they do not have hydrolyzable ions. Okay, so once those ions comes in contact with water, sodium plus with water, there will be no reaction. Chloride minus with water, no reaction. Why? Because these two ions, they are coming from a strong, the salt from the two of them, sodium chloride, is coming from a strong acid and a strong base. And because it's coming from a strong acid and a strong base, the ions are not hydrolyzable. They are not hydrolyzable. In other words, they cannot react with water. So when you have the salt of a strong base and a weak acid, the anion, which is the conjugate of the weak acid, it hydrolyzes to give a basic solution. In other words, when a salt is produced from a strong acid and from a strong base and a weak acid, the anion of that salt, okay, which is the conjugate of the weak acid, will hydrolyze a solution to give a basic solution. Okay, that is the cation, remember, because it's from a strong base, we give no reaction. So the sodium plus with water will give no reaction. Okay, but the anion, because it's coming from the weak acid, will undergo hydrolysis reaction to produce hydroxy ions in solution. And when it produces hydroxy ion in solution, that means the concentration of the hydroxy ions has increased. The solution becomes basic. Is that okay? So now we've talked about a situation, a pH of a solution where you have that is coming, the salt that is coming from a strong acid and a strong base. We say such ions are not hydrolyzable. The ions of the salt from a strong acid and a strong base are non-hydrolyzable. And so they cannot further react with water. And we've also looked at the situation of a salt that is produced from a strong base and a weak acid. And we said it will produce the solution to become basic. Okay, you have more of the hydroxy ion in solution. Now let's look at a case where the salt is produced from a weak base and a strong acid. Okay, now, in such a situation, the cation, which is the conjugate of the weak base, undergoes hydrolyzation. When a salt is produced and it dissolves in water, it gives you the cations and it gives you the anions. In this case, when the salt is produced from weak base and a strong acid, the cation is the conjugate of the weak base. And so it has the ability to undergo hydrolysis. And when that is done, it will make the solution to become acidic. Okay, so if you look at the reaction here, ammonium plus with water to give you the ammonium, which is a base, and the hydrozonium ion. So you have more of the hydrozonium ion in solution. And because the hydrozonium ion is more in solution, it will now make the solution to become acidic. That is a situation where you have a salt that is produced from a weak base and a strong acid. What about a situation where the salt is produced from weak base and weak acid, where both of them are weak? In this case, both ions that will be produced from the salt, okay, remember when it's a weak salt and a weak base react together, it will give rise to a salt, okay? When that salt is dissolved in water that go hydrolysis, it will produce both the cations and the anions. And the issue here is that both anions will undergo further hydrolysis. In other words, both anions and the cations will hydrolyze. And if they undergo hydrolysis, the solution may be basic or may be acidic. However, what determines whether the solution will be acidic or basic depends on the relative strength of the acid and the base, the relative acid-base strength of the two ions, the strength of the two ions in solution. Okay, now talking about the strength of the two ions in solution, how do we evaluate that? By knowing the Kb and the Ka. So if we know the acid dissociation constant Ka and we know the base dissociation constant Kb, then we can now know which of them is stronger. Is it the cations that are hydrolyzable or the anions that are hydrolyzable? Okay, so we now know from the Ka and the Kb whether the solution is acidic or the solution is basic. If the Ka is higher than the Kb, the acid is better at reacting with water and the solution becomes acidic. That is what it means. If the Ka is less than the Kb, the base is better at reacting with water and the solution will be basic. But if the Ka is approximately equal to the Kb, then the solution will be neutral, will be a neutral solution. It will be a neutral solution. So from here, from all that we've explained, remember we talked about when a salt is produced from a strong acid and a strong base, and we said the ions are non-hydrolyzable, okay? And we said when a salt comes from a weak acid and a weak base, and we said both of them are hydrolyzable, and the condition of the solution, whether acidic or basic, depends on their acid-base strength from the Ka and the Kb. Okay, so you can now decide where they may give you a question, give you a salt, strong, they'll give you a salt and tell you to decide whether that salt is acidic, basic, or neutral. Okay, so we have situation here, for example, here you are told decide whether aqueous solutions of the following salt are acidic, basic, or neutral. And here you have A, KCl, B, sodium fluoride, C, zinc nitrate, and D, ammonium cyanide. Okay, for the A, KCl, when it undergoes ionization, it produces the K plus and the K, the Cl minus. Remember, we say a salt of a strong acid and a strong base, both ions are not hydrolyzable. That is where we started from. Remember that. Okay. Now, if you look at the solution now of the salt will be neutral, because since both ions are non-hydrolyzable, then the solution will be neutral. Now, for the B, sodium fluoride, if sodium fluoride undergo ionization, it will give you the Na plus and the F minus. So the sodium plus is not hydrolyzable. We've explained that. The fluoride ion, anion will be hydrolyzable to give you more of the hydroxy ions in solution. And when more of the hydroxy ion in solution is given, then the solution is basic. Okay, so that of the zinc nitrate, the NO3 is non-hydrolyzable. The solution will also be acid because we produce more of the hydrosium ion in solution. So you have further questions here that on your own you can go through for further understanding. Okay, there are situations where they will give you the Ka and the Kb. You look at the values and see which one is higher. The one that is higher will determine whether the solution is basic or acid. Now let's look at the common ion effect. The common ion effect is a shift in equilibrium that is caused by the addition of a solute, okay, to the solution. And in such a situation, it will provide an ion that takes part in equilibrium. Okay, you have an equilibrium that is established for a reaction. Okay, possibly, for example, you have a particular salt undergoing hydrolysis. Okay, there will be an equilibrium that is established. However, when there is an addition of a solute that produces a similar ion that now participates in the equilibrium, it will affect the positioning of the equilibrium. It will shift the equilibrium either to the left or to the right. But in the examples that we are going to see, we will now know which of the direction is shifting the equilibrium. So when you have a salt undergoing hydrolysis to give you ions, and you now have another solute that is being added that is producing the same ions, either of positive or negative, that is the same, then that means that ion that is being produced that is the same will take part in the reaction. And if it takes part in the reaction, it will shift the equilibrium. That is what we mean by common ion effect. Okay, you have a salt undergoing ionization to produce the anions. Another solute is added. That solute undergoes ionization to now produce one of the same ions in solution. So if it is the same ion in solution, it will also take part in the reaction. Because it's the same, we say it's a common ion effect. Take, for example, acetic acid reacting with water. Okay, it will undergo ionization to give you the acetic anion and an hydrosonium ion. So if another solute now, for example, hydrochloric acid is added, is introduced, it will now produce, if hydrochloric acid undergo ionization, it will give you the chloride anion, the Cl- and the hydrosonium ion. So you now have the same hydrosonium ion that was produced when the acetic acid undergo ionization. So for the first equation, you have hydrosonium ion. For the second equation, you have hydrosonium ion when the acid is added. And what that means, the equilibrium position will be shifted. Okay, it will be shifted, and this will reduce the degree of ionization. It will reduce the degree of ionization. Similarly, if you have sodium acetate undergoing ionization, okay, it will produce the sodium plus and the acetic anion. Okay, the degree of ionization will be reduced. It will be reduced. The equilibrium will shift to the left according to the Le-Chatelier's principle. This is as a result of the common ion effect. The common ion effect. How do we calculate the pH of a common ion effect? Number one, you identify the strong electrolyte and you identify the weak electrolyte. Number two, you identify the major species in the solution, okay, the major ions that are in solution. Then you identify the equilibrium that is the source of the hydrogen ion, which is important. You know what determines pH is the hydrogen ion. So you determine the equilibrium source of that hydrogen ion from the equations. Okay, so you will now tabulate the ions concentration involved in the equilibrium, you tabulate them in the table as we'll see in the next slide. You tabulate the ions concentration involved in the equilibrium. Okay, from there now, you can now calculate the Ka. If you know the Ka, then you can now calculate the pH. How do we do that? Let's give an example. Let's explain an example here. Now, if you look at a question before us here, you'll see that the question says calculate the fluoride ion concentration and the pH of a solution that is 0.2 molar in hydrogen fluoride and 0.1 molar in HCl. Your Ka is given to you for hydrogen fluoride to be 6.8 times 10 raised to the power minus 4. So if you look at the equation for the fluoride when it undergoes reaction with water, and the chloride when it undergoes reaction with water, both of them will undergo ionization to give you a common hydrozonium ions. So you have hydrozonium ion in the first equation, you have hydrozonium ion in the second equation. And so if you write the dissociation constant equation, okay, for the first equation, you have the concentration of the hydrozonium ion and the fluoride ion, okay, over the concentration of the hydrogen fluoride. You know, Ka has been provided for you, 6.8 times 10 raised to the power minus 4. Because HCl is a strong acid, okay, so we'll rather use the concentration of the 0.2, we'll use the concentration of the 0.1, okay, because the HCl is a strong acid compared to the HF, which is a weak acid. So we use the concentration of the strong acid because the strong acid will override the weak acid. So we'll rather use the 0.1 molar. Okay, so in that case, we have 0.8 multiplied by 10 raised to the power minus 4 for the hydrozonium ion. We have 0.1 multiplied by S over 0.2. So if we work out that equation, you will now have the value 1.4 times 10 raised to the power minus 3. Okay, that is the concentration of our fluoride anion, the fluoride ion. So from there, we know that the hydrozonium ion is 0.1, okay, 0.1 plus S. If you look at the table there, like I said, you must first of all tabulate the concentrations of the anions and the acid. In that table, you see how it was tabulated. Okay, so you must bring out the table clearly of the changes that is taking place in the two equations. And so from there, you can easily evaluate the pH of the solution. So the pH, because the negative log of 0.1, and that will now give you the pH to be equal to 1. Okay, the same thing goes for this other calculation. You tabulate your tables and you use it for. So you practice the problems that are provided for you in the slide that has been given to you so that you can perfect and have a full understanding of this. Like I said before, if you need further explanation, you are having issues with some of these calculations, you can chat me up or WhatsApp so that or you get me in my office so that I will do further explanation. Now let's look at buffers. Buffer solutions. What are buffer solutions? What are buffer solutions? Let's quickly round up this. Also, buffer solutions are solutions that has the ability to resist changes in pH when a small amount of acid or base are added to it. So a buffer solution is a solution that has the ability to resist changes in pH when some small amount of acid or base are added to it. Okay, why? The reason is because the buffer solution contains an acid, so it has the ability to neutralize the OH, and it also contains a base. It has the ability to hydrolyze the hydrogen ion. Okay. So how do we calculate the pH of a buffer? So it is similar to the procedure for the common ion effect, very similar. Okay, so you consider the equilibrium constant expression for the dissociation constant of the acid Okay, we have an example here when HA undergo ionization in water, you will set up the Ka equation. So you rearrange it, okay, and you arrive at two important formula. pKa is equal to pH minus log of the anion over the acid. From there, you can make pH the subject of the formula. pH will be equal to pKa plus log of the anion over the acid. This equation is called the Addison-Eisenberg equation. It's very important to calculate the pH of a buffer solution. So you need to know this formula, the Addison-Eisenberg equation for the calculation of pH of a buffer solution is very important. So at this level, nobody will ask you to derive the equation of the Eisenberg equation, but you should know the formula and how to apply it. Okay, very quickly, there's a question here that says, what is the pH of a buffer that is 0.12 molar in lactic acid and 0.1 molar is sodium lactate? Okay, so these two equations, you write the two equations for the lactic acid and for the lactate, for the sodium lactate. Okay, so you will now use the Eisenberg equation to do the calculation. You already know your pKa value. Okay, you know the concentration of the anion and you know the concentration of the acid. And so if you use that value, you calculate the pH, it will be 3.77. So what is a buffer capacity and what is the pH range? A buffer capacity is the amount of acid or base that the buffer can neutralize before the pH begins to change to an appreciable degree. Okay, the amount of acid or base the buffer can neutralize before the pH begins to change. So the buffer capacity depends on the amount of acid base used to prepare the buffer. So the pH range is the range of pH values over which a buffer system works effectively. So it is best to choose an acid with a pKa that is close to the desired pH. Okay. So when you are adding an acid or a base to a buffer, then, like we said before, it is better to choose a pKa that is close to the pH, okay, so that there will be no, to the desired pH, so that you can have a good neutralization, okay, so that you can have a good neutralization. It is safe to assume that all of the strong acid or base is consumed in the reaction. Then you use the Addison-Eisenberg equation to determine the new pH of the solution. So there are a lot of examples for you, calculations that you will need to go through, and you know how to solve the pH using the Eisenberg equation. And so this is the end of the acid-base lecture, and I do hope that you follow the lecture closely. The slide will be provided for you, and take out time to study it. It's very important that you study it. And like I said, if you have challenges, find a way of getting across to me for further explanation. Any question? Any question? In the absence of any question, thank you very much. So I hope to meet each of you individually. For those of you that would need further explanation, thank you very much. God bless you. This is the end of the lecture for today. Oh, the buffer is not clear. We don't have much time. Like I said, get in touch. I will do further explanation. My office is opposite the Faculty of Science Annex building. Okay, the Annex building, the small building that is facing the Faculty of Science. Okay, when you enter the Annex building, you will find my office. The office is opposite the boardroom. Okay, there are 3 offices facing the boardroom. The middle office there is my office. So you can locate me in my office or get across with to be through my WhatsApp. We'll chat. I will explain further. Okay. My name is Dr. Lawrence Ekebafe. Thank you very much. God bless you. This is the end of the class for today. Thank you.